So here again, we're looking at relations, just like in the last video I ended off with. So here we have another relation. Again, a relation is just a collection of ordered pairs, and as it says up here, the collection of the set of all the first coordinates, which you can think of as the x coordinates, that's the domain. And the set of all the second coordinates, or the y coordinates in other words, that's the range. So for this example, 1 and 3, those are the first coordinates. The first components, mixed up the words, that's the domain. The second components, 2 and 4, that would be the range. Domain is 1, 3, this set, and this is the range. Also, from any correspondence diagram, you can, from any relation, you can draw a correspondence diagram. The idea is that you take an ordered pair, A, B, as I say here, and you just draw an arrow essentially from A to B. You can go the other way around as well. Namely, if you have a correspondence diagram, you could form a relation. Basically, each arrow from A to B would give you the ordered pair. Visually, you can have something like this. So let's say you had this was our first set, capital X. This is our second set, capital Y. So then if we had an A in here and we had a B, we have an arrow going from A to B, and that means the ordered pair AB is in the relation. And that's really what I'm trying to say here. So correspondence diagrams and relations, they are related to each other. Here's another example. We have this, 1, 3, 2, 4, 4, 6. So as I have over here already, the domain, again, is all the first components, or the x coordinates. You can think of it that way also if you want. So we have 1, 2, and 4. That's what the domain over here would be. For the range, we have 3, 4, and 6. Those are the second coordinates. And again, we can draw the correspondence diagram. Namely, here we have our x, which is our first set. Let's see if I can draw this. We have y, which is our second. We have 1, 2, 4, 3, 4, 6. So for the first ordered pair, we have 1 to 3. That's what this arrow gives us. For the second one, we have 2 to 4. That's what this gives us. And from 4 to 6, we have this. So we have a correspondence diagram from a relation. Again, they are related. Here's another example. We have this now. So now, what would the domain be? Again, the domain, this is all the first components. So as you can see from here, we have 1, 2, so 1 is in the domain. From the second ordered pair, we have a 5, 3, so 5 is in the domain. From the third ordered pair, 6, 9, 6 is also in the domain, so we have that. For the range, we have also, again, the second coordinates, the second components. So we have 2 from the first ordered pair, 3, and 3 from the second ordered pair, and 9 from the third. And just like before, it's good to be able to draw the correspondence diagram. We get to see these things visually. So we have 1, 5, 6, 2, 3, 9. 1 goes to 2. That's what the first ordered pair tells us. 5 goes to 3. That's the second. 6 goes to 9. That's the third ordered pair. Moving down. Now, there are a function is a special kind of relation. Basically, a function is a relation where no two distinct ordered pairs have the same first component. Or if you want, you could think of it just like we saw with correspondence diagrams, right? A relation is a function if the correspondence diagram gives us a function. Basically, what I'm trying to say here with the ABAC is that you can't have two ordered pairs whose first components are the same, but their second components are different. Because in that situation, this would happen. Let's say you had AB and AC were in the relation. So if this is X, this is Y. And if B were not equal to C, you have A here, you have B and C. Well, again, this is if B were not equal to C, you have A goes to B, but A would have to go to C. You would have something like this. And as we saw, for a function, each input, right, each element from the first set can only be assigned to one element from the second set. Going back to our input-output terminology, we need each input to have only one output. Here we have an input giving us two outputs. So again, for a relation to be a function, any two distinct ordered pairs must have different first components. Or if they have the same first component, their second component has to be the same. So if we went back to this example, this would actually be a function. We could see that from the correspondence diagram. We don't have to actually draw it because we can see from here, all three ordered pairs, they have different first components. So this would be a function. So that's what we have there. Moving on, here we have another one. So right now we have a relation definitely. Let's write out what the domain is. So again, the domain is all the first components. So we have 1. You don't want to list an element more than once in a set. So 1 is listed just once. And we have 3. So that's what the domain would be. Just to make it a little bit easier, let me put the range over here. So for the range, we would have the second component. So we have 2, right? We have 2 over here. We have 4 down here. And we have 5. So we have 2, 4, and 5. Okay, that's what the domain and range would be. And for fun, let's draw the correspondence diagram. So we have 1 and 3 in our domain. And in our range, we're calling that capital Y. We have 2, 4, and 5. So 1 is assigned to 2, right? That's what the first ordered pair tells us. For the second, we have 1 is assigned to 4. And for the third ordered pair, 3 goes to 5. And notice here, we have 1 being assigned to 2 different elements. And we saw that in the beginning, how we have 2 different ordered pairs here. Okay, let me see if I get the pointer right. We have 2 ordered pairs here, but their first components are the same. And their second components are not. In other words, we have 2 different ordered pairs with the same first component. Thus, this is not a function. It's a relation, but it's not a function. Let's do this example. So here, let me just, as above, I'll put the range over here on the right side. But here, the domain, so we have 1, that's a first component. We have 6, and we have, not 4, we have 3. So that's what our domain would be. Our range, what is that going to be? Well, we have 2, right? That's a second component. We have 4, and we have 5. So just like above, we can draw a correspondence diagram. See if I can fit it here. We have 1, 6, 3. We have 2, 4, 5. So this is our X. Here's our Y. So from the first ordered pair, 1 is assigned to 2. From the second one, 6 is assigned to 4. Here, 3 is assigned to 5. And this is a function. We can see that because, again, each of the ordered pairs have different first components. And we could see this also from the correspondence diagram, that each input, each element from the first set is assigned to only one element from the second. Unlike up here, where we have an element assigned to more than one element from the second set. So here we have an input that has 2 outputs, whereas in this example, of course I could do that, we have an input, but each input, has an output, only one output.